perimeter is the length of the line that bounds a figure. It is measured in linear units. The area is the two-dimensional region bounded by a figure. It is measured in square units. If we look at our first example is a rectangle. So the perimeter of this rectangle is the length of the line that goes around this rectangle. It is the length of the line that bounds this figure. If I cut this rectangle and laid this entire line flat, how long would that line be? That's my perimeter. So if I start here to go all the way around to bound my figure, I'm going to go 1, 2, 3, 4, 5, 6, 7, 8. In reality, I'm going to go 1 plus 3 plus 1 plus 3. You might have seen the formula for the perimeter of a rectangle as 2 times the length plus 2 times the width. Well, I'm really taking 1 plus 3 plus 1 plus 3 for a grand total of 8 units. If each one of these lines is 1 unit apart, it's going to take me 8 units to bound this figure. The area is the two-dimensional region inside of this figure. I'm going to measure the area in square units. So how many squares fit inside this rectangle? Well, if I look, there's 1, 2, 3 squares. Or I can use the formula for the area of a rectangle, which is length times width. The length of this rectangle is 1, and the width is 3, so my area is 3 square units. In example 2, to find the perimeter, I need to find the length of the line that bounds my figure. So if I start here, 1, 2, 3, 4. 1, 2, 3, 4. Now if I connect diagonally, 1, 2, 3, 4. But if I look, when I connect diagonally, I'm actually going further than if I connect horizontally or vertically. The length diagonal is longer. The question is, how much longer? Well, if I look at this small right triangle right here, it's an isosceles right triangle. If this side is 1 and this side is 1, this hypotenuse is going to be longer. How much longer? Well, it's going to be the square root of 2 times longer. And this length from here to here is going to be the square root of 2. And diagonally from here to here is the square root of 2. And diagonally from here to here is the square root of 2. So my entire length diagonally is made up of 1, 2, 3, 4 square roots of 2. Which makes sense if I look at this big triangle as an isosceles right triangle, 4, 4, 4 square roots of 2 for my hypotenuse. Remember, in a triangle on a geoboard with square pegs, diagonally is going to be longer than vertical or horizontal. So my perimeter is made up of 4 plus 4 plus 4 square roots of 2. Now what can I combine in this statement? These first two 4s are just integers, so I can add those like terms. My last term, 4 square roots of 2, even though there's a 4 here, I cannot add 8 plus 4 and get 12. This 4 is really a coefficient. It's keeping track of how many square roots of 2 I have. I have 4 square roots of 2. So this integer and this irrational number are unlike terms. So my perimeter is 8 plus 4 square roots of 2 units. If I wanted to find the area of this shape, I need to find out how many squares fit inside of it. So I can just count. Here's one full square. Here's another full square. Here's another full square. Plus another full square and another full square and another full square. So I have 1, 2, 3, 4, 5, 6 full squares, and if you look, I have 1, 2, 3, 4 half squares. So I have 6 plus a half plus a half plus a half plus a half gives me a grand total of 8. Or I can use the formula for the area of a rectangle, or excuse me, the area of a triangle. A triangle is half of a rectangle. So the formula is going to be 1/2 length times width. But I'm not going to call the length of the triangle its length. I'm going to call it the base. And the width, I'm going to call the height. So my area in this case is actually going to be 1/2 times 4 times 4, which is 8 units squared. To find my base, I need this measurement, this length, and my height is this length. Notice that the base and the height form a right angle. So the area is 8 units squared.